Alright, so for our first sample problem, this problem is taken from the textbook or reviewer text by Bautista, Fundamentals of Pumps, Fans, Blowers, and Compressors. And this is actually it. Right, so fundamentals of pumps, fans, blowers, and compressors. And this is Anthony James Bautista. The problem says that um, air enters a fan at an initial velocity of 7 meters per second and a static vacuum pressure head of 22.5 millimeters of water. The air is delivered at a velocity of 12 meters per second and a static pressure head of 81 millimeters of water. The fan has a capacity of 9.5 cubic meters per second and is coupled to a 15 kilowatt motor. Determine the total air power if the density of air is 1.2 kilograms per meter cube. Right, so there's no figure that's given, so therefore for our first step in the solution we have to convert this word problem into an illustration. Right, so for the solution, first step is illustrate the problem. So let's say here's our fan and here's our fan blades. Then of course there's gonna be flow. So point one, let's say that's the suction side, and right here's the discharge side. Right. So at point one, it says here that we have it says here air enters a fan at an initial velocity of 7 meters per second. So therefore, V1 is equal to 7 meters per second. And it says here the air is delivered at a velocity of 12 meters per second. So for our point 2, that's going to be 12 meters per second. And what else? It says here air enters the fan at an initial velocity of 7 meters per second and a static vacuum pressure head of 22.5. So take note of this word. This is static vacuum pressure. That means from the reference of atmospheric pressure, then that's going to be negative pressure. So this will be negative 22.5 millimeters. But now let's convert that to meters. What we get is P sub 1 is equal to negative 0.0225, right, meters. And for the pressure head at point 2, what we have is 81 millimeter. So this is 81 millimeters. Right, so what else? Um, it also tells us the flow rate, which is, so Q is equal to 9.5 cubic meters per second, and it also gives us the power. That's power of motor. Take note, this is not the air horsepower, but rather it's the electric, um, or it's the power for the electric motor input, right? So it's not the brake horsepower, and it's also not the air horsepower. So this is 15 kilowatts, and for our density of air, it says 1.2 kilograms per cubic meter. Right, so that's it. So now let's solve for the um, we are only asked to solve for the total air power. So if we solve for that, we need to calculate the static and velocity head to obtain the total head. Right, so ht is equal to hv plus hs, and hv, we know that hv is just simply v2 squared minus v1 squared all over 2g, and this is 12 squared minus 7 squared all over 2 times 9.81. So this is 12 squared minus 7 squared divided by 2 times 9.81. This is 4.84. So 4.84 meters. Okay, next one is H sub S is, take note that our pressure is in terms of head, but this head right here, this is actually the head of water, right? So what that means is, if we have here, let's say we have a YouTube manometer, right? So also right here we also have YouTube manometer. Then right, so if here's our YouTube manometer, okay, so this is it. Actually, the fluid right here is an is an air, but we have a manometric fluid of water, right? So that means that this rise right here is referring to the unit weight of the water. Okay, so therefore we need to, or if we use this equation, p sub 2 minus p sub 2 minus p sub 1 all over this. Of course, this should be the unit weight of air, but this pressure is given in terms of head, so therefore this is going to be h sub 2 minus h sub 1. Of course, with this one, with this unit weight, but this one is the unit weight of water. So since the unit weight of water is the same, so let's factor this out. Then what we're left is h2 minus h1, and this is all over the unit weight of air. Okay, so for the unit weight of water, this is 9.81 times 1000, so this is 8810. This is Newton per meter cube, and this one is 81, or 0.081 minus, take note, minus negative 0.0225, minus negative 0.0225 all over the unit weight of air, which is just, let's just write 1.2 times 9.81. Right, so let's do that. 0.081 minus negative 0.0225, right, times 9810 divided by 1.2 times 9.81, and this is 86.25 meters. Right, so therefore the total pressure is HT is equal to HV plus HS, which is just simply 4.84 plus 86.25 meters. So plus 4.24. This is 90 point, 4.84. 4.84 plus 86.25. So this is 91.1. 91.1 meters. Right, so that's our total fan head. Therefore, solving now for the total air horsepower or air power, total air power. Right, so AP total is just equal to the flow rate times this unit weight of air times the total head, and our flow rate is 9.5 cubic meters per second times the unit weight of air. This is just 1.2 times 9.81, and that's gonna be Newton per meter cube, and then times the head of 91.1. So this is 91.1 meters, and if we do this times 1.2 times 9.81 times 9.5, and this is 10.2 or 10,000 in terms of watts. Let's write it down: 10,186 watts or 10.2 kilowatts. Right, so that's it. So now let's try, let's do this, trying now the conservation of energy. It's actually the same thing, because recall, if here's our fan, and then let's say here's our system boundary, and we have this inflow, we also have this outflow, and we have these losses, and we also have this input H blower or fan. Okay, so we have this flow in, and we also have this flow out, and this is P1 by gamma plus P1 squared all over 2G plus Z sub 1, and this is P sub 2 all over gamma plus V sub 2 squared all over 2G plus Z sub 2. So basically, the equation is H fan is equal to P sub 2 minus P sub 1. Of course, this is air, plus V1 squared all over minus V2 squared all over 2G plus Z sub 2 minus Z sub 1 and plus H sub L, right? And this is 0. This is also 0. And therefore, if we do that, actually, this is the same equation. This is exactly the same equation as this one for the HS. So this is 86.25. And for this one, the velocity, this is 4.84. That's 4.84. And therefore, our total is 91.1. So this is 91.1 meters. All right, so I think that's it. Then let's do another sample problem. Okay, so our next sample problem is again taken from the same reference, fundamentals of pumps, fans, blowers, and compressors. And the problem says here, determine the brake horsepower required for a fan with a static efficiency of 50% and delivers air at 1200 CFM. Static pressure developed is 2.5 inches of water and air is at 60 degrees F, and a barometric pressure of 30 inches of mercury. Okay, so for the solution, um, again, since there's no illustration, then we'll try to make illustrations for this problem. So first step is to illustrate the problem. So let's say here's our fan, and we have this inflow, of course, and we also have this outflow, right? Except that we don't need that. We'll just use this. And it says here, determine the brake horsepower required for a fan with a static efficiency. So this is N sub S, or eta. S is equal to 50%, and Q is 1200 CFM. And it says here the static pressure developed is static pressure, or let's just write HS is equal to 2.5 inches of water, H2O. Okay, so if we think about it, we are asked to solve for the brake horsepower. And recall that when we say brake horsepower, that's the let's say here's our fan, and let's say here's the electric motor, right? And in this fan, let's say we have this hub, and then we also have these blades right here. And here's our electric motor. When we say air horsepower, that's the horsepower, or the power delivered to the air, so that the air can move from one location to another or across a pressure difference, right? So that's the air power. But when we say brake horsepower, that refers to the horsepower delivered by this shaft right here. So that's the shaft. So there's going to be a brake horsepower, bhp. And when we say electric motor or power input, that refers to the input power to the electric motor. So this is, let's say, power input, right? So power input, then of course, let's say if this is 10 kilowatts or 1 kilowatt, then the brake horsepower, because there are losses, let's say frictional losses inside this electric motor and inside this assembly, then that means if our power input is 1 kilowatt, the brake horsepower would be less than 1 kilowatt. So this is, let's say this is 0.8 or 0.9, let's say. So if this is 0.9, this is 1.0, then there's going to be efficiency from the brake horsepower to the air horsepower, another efficiency. So therefore, let's say this one would be around, let's say 0.5. So again, from this power input to the electric motor, required power input, there's going to be efficiency, and that's a another efficiency. And from the brake horsepower to the air horsepower, it's there's also another efficiency, right? So again, from this power input is 1.0, but because of frictional losses, then there's gonna be a reduction of 1.0 to 0.9, and the power available to our shaft is what we call as the brake horsepower. And from the brake horsepower to the air power, there's also going to be losses because there's going to be efficiency. So from 0.9, let's say it goes down to 0.5. Right, so therefore we have three different terms for now. Okay, so let's continue this. And what else? Air is at 60F. Let's just write it here. Air is 60F and barometric pressure of 30 inch mercury, HG. Okay, so since we are only asked to solve for the brake horsepower, let's solve first for the air horsepower. But of course, since this is static, then that means we solve for a static air power. So this is Q times this unit weight of air times the static head. So Q is equal to, what is this? 1200 CFM. That's cubic feet per minute, right? And times this unit weight of air, but take note we are in English units, so this is 62.4 pound force divided by feet cube, or let's just write this feet cube per minute. Right, so feet cube per minute. And for the static, this is 2.5, right? 2.5 inches of H2O. 2.5 inch, and since this is in feet, then let's convert this to feet. This is 12 inches per foot, and therefore 1200 times 62.4 times 2.5 divided by 12. So this is 15,600. So 15,600. So the units would be, since this is feet cube, this is also feet cube. What else? This is inch and inch. So what's left is pound foot per minute. So pound foot per minute, that's actually a unit of power. And the conversion to HP is, take note of this conversion. So we have 1 HP is equal to 550 pound foot, pound, of course, pound, that's going to be pound force, but pound foot per seconds. And since this is in seconds, this is in minute, then let's convert this to seconds. That's going to be times 1 minute per 60 seconds. Right, so this is 15,000 divided by 550 divided by 60. This is 0.47. This is 0.47, what else? 473 HP. Okay, so again, just take note of this conversion factor. Or let us write it here. So 1 HP is equal to 550 pound foot per minute, sorry, per seconds. And if we convert this, what we get is 550 times 60, that's 33,000 pound foot per minute. And another one is, in terms of kilowatts, this is 0.746 kilowatts. Right, so that's our conversion. Okay, so moving on for step number 3. Therefore, we can now solve for the brake horsepower. And recall the equation BHP is equal to air horsepower. And since we are using static air horsepower, then the efficiency that we'll use must be also be in static times, I think times 100. No, that's just it. Okay, so let's substitute. Air power is 0.473 HP divided by the static efficiency of 50%. So this is 0.5. So this is 0.473 divided by zero point 0.5. This is 0.946 HP. And of course, this is just a value with respect to computations, but of course we need to adjust this. I mean, adjust this if we are going to select an electric motor. Of course, we need to adjust that. We need to know the efficiency or assume some efficiency values. Right, so I think that's it. So let's go back now to our lecture materials. Let's continue the remaining subtopics regarding these fans and blowers. So we haven't discussed this, or will not discuss this anymore. The fan specific speed, and we'll move on to this fan loss.